much for the nice introduction. My topic for today is about Open ASIP and how to design customized processors with it. So we're talking about ASIPs. They're also called application-specific instruction set processors. And the idea is that you customize the instruction set for a set of target applications. And the main motivation is that you can achieve better performance and energy efficiency in this set of priority applications. And doing all of this manually, so you have to program them and design them, it's quite a lot of work. So most often you want to rely on hardware-software co-design toolsets. But often these are proprietary, which is of course not nice. And from this point, we get to Open ASIP. So it's an open source solution for designing and programming these customized processors. Traditionally, it has been targeting so-called transport ticket architecture, so TTA. And it's an exposed data path processor, so it has a very low-level programming interface and lots of scheduling freedom. And the toolset has been developed for a very long time, so over the years it has accumulated quite a bit of support for designing and programming these customized TTA processors. So it has a retargetable compiler and also hardware generation down to RTL. TTRs are pretty great, but we thought it would be really nice to also support other architectures, so we wanted to add support for the RISC-V ISA. And the idea is pretty much the same, so we want to program these customized RISC-V processors and also generate RTL from this high-level description. And here we actually have an example of the design flow. So there's one central processor description called architecture definition file. And it describes everything that's visible to the programmer, so in this case, the compiler. And it's a very modular description. So what it does, it references operation entries from separate operations at databases. And the idea is to have high design reuse. So you can reuse operation descriptions for multiple architectures. And the ADF, so the processor description, it's also passed to the compiler and to the RTL generator. And this way we can retarget the tools. And here's roughly how the compiler adaptation works in the current upstream version of the toolset. So we rely on the RISC-V LLVM backend. And currently, we only support using so-called intrinsics. So they're essentially wrapped inline assembly blocks. And how we do the retargeting is that we load OpenASIP as a dynamic library just before code emission, so as so-called pre-emit pass. And it converts these inline assembly blocks to instruction encodings. So when you generate the machine code, you have your correct encoding for your custom instruction. The downside of this approach is that you don't have automatic instruction selection. So the backend is not aware of your custom instruction semantics. But the upside is that you don't have to recompile and generate the compiler backend when you change architectures. But behind the scenes, we've been working on improvements to the compiler. So in the future, also this instruction selection will be supported. And it's achieved by generating new compiler backends from the architecture definitions. In terms of operation descriptions, there's essentially two ways how to add new custom instructions. And the more convenient way is so-called operation DAGs, so directed acyclic graphs. And the idea is that you use basic operations to describe the semantics of your new custom instruction. So here we have an example where we combine rotation, shifts, and XORs to form this sigma function. And it forms this graph structure. And I think this is quite a convenient way for describing operations. There's also another option, so you can use RTL directly to describe your operation semantics. And sometimes this is needed if you have very complex patterns that form loops, for example, so you couldn't describe those as a acyclic graph. And here we have also an example of this kind of operation description. And the toolset, it also supports the hardware generation down to RTL, and somewhat of a multi-problem because you have to generate the processor pipeline, which is quite static, but then you have also this customized functionalities that the designer can choose and describe. And we have a separate tool for generating these customized function units that can vary a lot based on the designer's input. And what it does, it changes these basics operations from the doc descriptions, and for the HTTP snippets, it embeds them in the function unit pipeline. And it can also automatically add register pipelines for your operations based on the latency parameters that the designer can choose. And when the function unit is generated, it's integrated into the rest of the processor pipeline automatically. Now that we have a good idea what the tool can do, we can go through this simple case study example. So we can design an ASIP for the secure hash algorithm. And usually you have to divide these to 4 different steps. So first, of course, you have to know what your operation candidates should be. Then you add these entries to an operations database. Then you modify your architecture description to include these operations. And finally, you can modify the application source code to invoke the custom instructions with the intrinsics. In case of the secure hash algorithm, there's 4 interesting candidates, and nowadays these are actually part of a standard extension. So there are these sigma and sum functions that combine these rotations, XORs, and shifts. And these are quite interesting for ASIPs because the hardware complexity of these operations is very low, but if you were to compile this down to the standard ISA, it would be fairly complex already. And these operations, they form these hot loops in the program because they're invoked a lot. And here we add these operations to a new operations database. And we can describe the operations as docs because they just combine different basic operations. Now that we have added them, we can also add them to our architecture description. So here we add these 4 new operations to the ALU. And we also add them to the correct instruction format. Now that we have a valid architecture, we can modify the application source code. So here we add this intrinsic call. It's basically this macro function that wraps the inline assembly. And the downside currently is that you have to invoke this manually, so the compiler cannot compile or invoke your custom instruction directly from the C code, but in the future release of the toolset also this instruction selection will be supported, so the designer doesn't have to do this step anymore. But sometimes this is needed anyway, because if you have a very complex operation pattern, the compiler might not be able to select it, so if you want to guarantee a good quality of results, you might want to invoke these intrinsics manually anyway. Now that we have everything else taken care of, we can generate the actual processor RTL, and to do that we invoke a command line tool, and it will invoke the function unit generator and generate this custom function unit based on the operation docs. And it will also generate a decoder for us that recognizes the encodings for the custom instructions. Now, when we have the processor RTL and our application, we can synthesize it and run RTL simulation. And if we do that, we see that the execution time is roughly cut in half, but there's very little overhead in terms of area and clock frequency because the operations we were describing, they're very simple to implement in hardware. And we could do all of this without writing any RTL ourselves, so if you don't know hardware so well, this is a very good approach for designing processors. As future work, we plan to integrate the hardware generation flow with the CVX interface, and this is a standard coprocessor interface. I think there was a talk about it earlier. And this way we could design custom instruction set extensions for any RISC-V processor that implements this interface, and you also get the compiler support from OpenASIP. And we're doing this in the Tristan project. And like I mentioned earlier, we're also working on this backend generation problem, and it will be upstreamed in the future release. And that way we get automatic instruction selection support. So in conclusion, OpenASIP is a hardware-software co-design toolset, and you can design RISC-V ASIPs with it, and also TTA ASIPs. And it has a retargetable compiler, so you can program from C, and it will use your custom instructions. when you invoke them. And there's also support for RTL generation from this processor description. And it's quite modular, so it has different components, and the idea is that you have high design reuse between different architectures. And you can do all of this without using any RTL. Yeah, it's on GitHub, so you can go test it out. I want to thank you for your time. I think we might have still time for questions.
Yes, Carrie, thank you very much. So we do have time for 1 or 2 questions. The microphones are roving. Can you put your hand up if you'd like to ask a question? In the front here.
Hi, yes, Nicolas from Bosch. Which core do you think you will target to demonstrate the generation with the CVXIF?
Did you mean this?
For the last slide.
Last slide, FutureWorks, the FutureWork item you had.
Last
one.
Your summary.
Yes, yeah, there.
Yeah, the previous one. Go ahead.
Okay.
Before.
One back.
One back, yes.
That's it, the first bullet.
Okay.
Generate for CVXIF.
All right, okay. So we're using CVA6, so it has some implementation for the CVX interface. Yep.
Okay. Any other questions? Yes, just over there.
Thank you for the talk. What restrictions do you have for custom instructions? The schematic says it looks like any other instruction, like 2 inputs, 1 output. Is that major constraint, or you can do more than that?
You mean the stack descriptions?
Yeah.
Or your example, the code example. But the custom functional unit can have arbitrary inputs or arbitrary outputs in number?
Sorry, I didn't really hear the question.
When you design an instruction, are there any constraints on the number of inputs, number of outputs?
Right, okay, yeah, that's a good question. Yeah, currently it's restricted to the R format, so you need to have 2 inputs and 1 output, but we're doing the compiler improvements, and then there's more freedom in terms of addressing modes. Yeah, that's a good question. Thank you.
Any more questions? Wave your hand vigorously. I've got the light in my eyes. No? Okay. I have a question for you then. Okay. You're now doing RISC-V. Previously, you did transport-triggered architectures, TTAs. Right. They are very, very different. Which do you find better? What do you get the best results with?
I have no favorites. RISC-V is obviously better for general-purpose computing that has branching code, for example. And these TTAs, they're usually used for DSP applications, for example, where there's a high amount of static instruction-level parallelism. So in those scenarios, TTAs can really shine, but they're not as efficient in general-purpose computing as RISC-V.
Okay. Okay. So, Kari from Tampere in Finland, thank you very much indeed.